Okay. Awesome, thanks. Thanks a lot for the kind introduction. Well, Happy New Year, everyone. And thanks for the opportunity to present my work. So I arrived in Waterloo around 3 months ago in October. So far it's been great. So hopefully soon we will be able to resume the seminars in person and enjoy some pizza and coffee as well. But for the moment, I just want to give you a brief overview of my work, which is related to the large-scale structure of the universe, the cosmic web, and how can we get better cosmological constraints by exploiting the cosmic web information. This background image is actually a representation of the cosmic web generated by a neural network. If you are on Twitter, you have probably seen this before. So you can type the name of your research in this website here. And this artificial intelligence based on neural networks will try to interpret those words based on the training data, right? And I think this is a pretty spot-on representation, pretty cool representation of what the cosmic web might look like if we could see it at its full extent and glory. So you can give it a try after the seminar or during the seminar if you get bored, but I will try my best to avoid that. Now, even though humanity has existed for only a fraction of a second, if we place ourselves in a cosmic calendar, our understanding of the world around us has taken many different shapes and forms. So there have been different cosmographic systems, such as the ones introduced by Ptolemy, Copernicus, or Tycho Brahe, which have definitely changed our conception of how vast and intricate the universe around us really is. These are the examples that are most usually cited. But of course, there is a plethora of different cosmovisions throughout history, many more than the ones I can exemplify here. Often those are also intertwined with the cosmogony and the myths of creation, which are of course a very interesting subject by their own. So maybe in the future we can also invite a person who can talk about in more detail about all these different cosmovision and cosmographic systems. Now, doing a huge leap into the future, this are some examples of how our understanding of the universe that surrounds us and how these maps of the universe and the large-scale distribution of galaxies have evolved across time over the last few hundred years. So these plots exemplify the mapping of the large-scale distribution of galaxies. So in each of those points, in each of these plots, each dot represents a single galaxy. So on the top row, from left to right, we have the first observations from the CFA redshift survey. Then we have gamma in the middle, and then on the right we have vipers, and on the bottom row we have SDSS BOSS, and then the extended BOSS at high redshift EBOSS, and on the bottom right we have the prospect of what we will hope DESI will bring in the future. So definitely our understanding and our awareness of how vast the universe is has changed, and our understanding nowadays is that the universe evolved from a very homogeneous initial state to the highly complex structures we see nowadays. So under this model, the cosmic web assembled in a hierarchical structure formation scenario where small-scale quantum fluctuations from the early universe grew due to gravitational instabilities. This movie is showing a fly through one of the Eagle hydrodynamical simulations, which nicely highlights the way in which the complex pattern of the cosmic web assembles over cosmic time. Eventually, these structures also hosting galaxies that live in the peaks of this density distribution. Now, when it comes to putting constraints on all the possible different cosmological models out there, understanding and measuring this cosmic growth history is very relevant. Dark energy, for instance, suppresses the growth rate of cosmic structure, which is described by this linear growth factor here on the y-axis, right? So, for instance, if we want our lambda cold dark matter model, which includes dark energy, to fit the clustering that we observe nowadays, the growth factor in this model must have been larger in the past than in other models which do not include as much dark energy. So by measuring the clustering at different epochs, we could also put constraints in our models and get precise estimates of the composition of the universe, as well as shedding light on the validity of the theory of gravity on very large scales. One of the best ways we have to actually measure the growth rate of a structure at different redshifts is through the so-called dynamical or redshift space distortions. So in order to build these 3D maps that I showed you earlier, we need to estimate the distances to galaxies. A reliable way to do this for very large volumes and distant galaxies is to measure the redshift of a galaxy and adopt a certain model to map those redshifts into covariant distances. In doing so, we assume that the recession velocity of the galaxy that produces that redshift is only sourced by the cosmological expansion or the Hubble flow. But in reality, however, the galaxies also have peculiar motions due to their interactions with other nearby galaxies and structures. And this perturbs the measured galaxy redshift and introduces anisotropies in the distances and in the clustering measurements. So while two galaxies might be separated by a distance r in what we call the real space, in the observable or the redshift space, we will observe that they are separated by a distance s instead. And this, of course, induces anisotropies and distortions in the clustering that we measure from these galaxy samples. So for instance, structures that appear or structures that are in fact spherical in real space, they will appear to be elongated or squashed in redshift space, depending on what their density profile is. So overdensities such as galaxy clusters, in which the galaxies are coherently falling towards the center of the potential well at large scales, they will look squashed on very large scales. And this is an effect that is also known as the Kaiser effect. For underdensities, on the other hand, such as cosmic voids, in which the galaxies are receding away from the centers of these structures, the voids will appear to be elongated along the line of sight on very large scales. This can clearly be seen in the two-point correlation function when we plot it as a function of the distance perpendicular and parallel to the line of sight. So in this kind of plots, the contours basically show the amplitude of the correlation function as a difference of these two separation vectors. And of course, in the absence of redshift space distortions, these contours would be perfectly symmetric around the center, right? But in practice, we do see that there is this squashing on very large scales along the line of sight due to the Kaiser effect. And you can see that on small scales, instead of squashing, we have this elongation along the line of sight. This is an effect that originates from random virial motions of galaxies near the centers of these overdensities. This is usually known as the fingers of God effect because this distortion makes these 3D maps look like these massive fingers when you look at it this way. So this is why people just start calling these fingers of God. To make it consistent, they also call the Kaiser effect at large scale the pancakes of God, because why not? So we have these two effects distorting our clustering measurements. The Kaiser effect is more of a large scale effect, whereas the fingers of God can be across a wide range of scale because it's a much stronger effect. The cool thing about these distortions, though, is that we can model them and we can understand something about gravity, because the peculiar velocities of galaxies are ultimately sourced by gravity itself, right? So by modeling them, we are in fact modeling the growth rate at which the cosmic structure is assembling at a given epoch. These 2D plots on the left are nice for visualization and getting an intuition of what is going on. But when it comes to making statistical tests and putting constraints in the model, it is much more convenient to decompose this correlation function into multiples, such as the monopole, quadrupole, and hexadecapole. And then compare the data against the different models for different gravity theories or different cosmological parameters, right? No, this is slightly more complicated in practice because apart from the redshift space distortions, which are of dynamical origin, we also have this second class of distortions called Alcock-Paczynski distortions, which are distortions that are geometrical in nature. These distortions arise because we need to specify some cosmological parameters when we map redshifts to distances using a particular redshift to distance relation, right? Namely, most importantly, the matter density parameter. So if the value of those cosmological parameters that we use to map redshifts to distances are not the true or the correct values of the universe, then we will artificially introduce distortions in our clustering measurements as well. Fortunately, we know how to properly account this in our clustering analysis. But it's important to model this simultaneously with redshift space distortions, because this can produce effects that can have degeneracy between each other. So they can be degeneracies between RSD and AP. So it's important to model them at the same time in order to get reliable cosmological constraints. So by modeling RSD in the two-point correlation function, or also in its Fourier space analog, which is the power spectrum, different teams have been tremendously successful at measuring the growth rate at different redshifts. So these plots compare results from different projects, such as the 6-degree field galaxy redshift survey, Gamma, WCA, SDSS. And with these data sets, people have achieved between 5 and 10% precision in the parameters that encapsulate the information of the cosmic growth rate at different redshifts. And it is expected that stage 4 experiments will provide or will push these to even lower limits down to % level precision. So that's all looking very promising indeed. Now, here's a trick. So even though the two-point correlation function and the power spectrum have been pivotal in the development of large-scale structure and cosmology for more than two decades or even more now, we have to keep in mind that they cannot fully describe the density field when we go to very small scales. This is a recent plot by Janes Nasto, where he basically shows the evolution of the density PDF at a scale of 4 megaparsecs, so very, very small nonlinear scale, as a function of redshift. So even though the distribution or the PDF starts very close to a Gaussian distribution at high redshifts, it quickly evolves into a PDF that has a significant kurtosis and skewness at later epochs. And since the two-point correlation function and the power spectrum are basically a measure of the variance of the density field, they cannot fully describe the density field if it's non-Gaussian and has this huge...
Can I ask a question, Enrique?
Of course.
Yeah. So do you, I mean, people must have looked at the distribution of log of 1 plus nu, right? Which is, because 1 plus, I don't actually, it's not 1 plus nu, it's 1 plus delta, I guess. So nu, you're normalizing by the variance.
Yeah, I think yeah, this one is normalized by the RMS. So you start from a mean of 0 and minus is 5 sigma. So yeah, I mean, people
So
have
I was
also
just
tried.
basically, I'm just wondering if you plotted in the log scale, would it look much more Gaussian? If instead of nu, you looked at log of nu, or I guess a log of 1 plus delta, that would be the more appropriate thing.
Yeah, I guess if you plot it on log scale, it would look slightly better. And this is in fact some transformations that people actually use in the literature to remove some of the nonlinearities in large scale structural distribution. So they apply this log transform to the density field before using their method, their statistical method to extract cosmological information. This is something people actually do. It doesn't fully solve the problem, but it does help in some contexts. So yes.
Okay. Cool, thanks.
Right. So one way to access this, well, basically, as the two-point correlation function won't fully describe this PDF at very small scales. Some of the cosmological information is leaking out to higher orders, right? So 2 or 3-point correlation function, 4-point correlation function, bias spectrum, and so on. So one way to access this information is, of course, to measure these higher order n-point correlation functions. But another way to do this is to basically look at other clustering statistics from the cosmic web, such as the cross-correlation function between voids and galaxies, or clusters and galaxies. So for instance, the plot on the left is a plot by the team led by Sachin Adathur, Alex Wood-Finden, and Will, who have shown that by incorporating the cosmological information coming from cosmic voids in the BOSS survey, they were able to improve the cosmological, the precision on some cosmological parameters, the growth rate, and most importantly, the parameter that constrains the Alcock-Paczynski distortions. So they find that by incorporating the information from the voids alone, they can improve the estimates by nearly 40% when added to the usual BAO plus RSD information, which is definitely quite promising. On the right, it's a recent paper by Marulli et al., where they basically incorporate the information coming from the clusters correlation function. Again, adding information from these different cosmic web components added together with information we already have from the two-point correlation function seems to tighten the constraints, which is telling us that incorporating information from other cosmic web environments is also helping us to access this higher order information that is lost in the process when we go to very small scales. The cosmic web, as we already know, is in fact comprised of multiple components, as shown by this plot from Marius Kaltun in 2014. So the voids account for more than 70% of total volume of the universe, which is huge. But when it comes to mass fraction, most of the mass seem to be contained in filaments and walls. The thing is that the two-point correlation function by itself, it naturally puts more weights on regions of very high number density of galaxies, because that's where most of the galaxy pairs actually are. So you are kind of overweighting the overdense regions with respect to the rest of the cosmic web. So a way around this, as I previously mentioned, is that apart from the two-point correlation function information that will highly contain information from these nodes of the cosmic web, you can also incorporate information from voids, for instance, or cross-correlation functions from different cosmic web environments. And this is sort of what we have proposed for improving the precision of RSD analysis. We basically propose to split the galaxy density field at small scales in different density bins, which have more or less a fixed galaxy number density. And then we model the redshift space distortion components in each of these environments separately and combine their constraining power during the likelihood analysis. So the pipeline more or less works as following. So you need to start from a distribution of random points in your cosmological volume. So you just throw a bunch of random points into your survey or simulation. Usually have a couple of million random points is fine. And then you measure the integrated galaxy density around each of those random points using a top hat filter with a given radius. And then you basically divide all those random points or classify them into different quantiles according to what their local galaxy density is. So you end up with a plot that will look like this, where the histogram is just the density PDF at the scale of 50 megaparsecs, and the different colors denote the division of this PDF into different quantiles, where each quantile will have the same number of points, but more or less fixed number density, local galaxy number density. And then once you split the density PF, the next step is to basically compute the cross correlation function between the centers of each of these points and the entire redshift space galaxy field. So this way you will end up with a sample of void galaxy cross correlation functions, cluster galaxy cross correlation functions, and also cross correlation functions of all of the stuff that is in the transition stages between voids and clusters, namely all the filaments and all the walls of the cosmic web that are in between these two extreme environments, right? And the goal is to model the redshift space distortions and the Alcock-Paczynski distortions in each of those bins in order to hopefully improve the cosmological constraints. This is in fact very similar to a concept people use in weak gravitational lensing analysis, which is called density split statistics, where they basically divide the observed area in the sky in different patches according to the fixed, according to the foreground galaxy density. So they end up with all these different patches of more or less fixed foreground density, and then they compute the shear, the weak lensing shear signal for each of those quantiles separately. And they have found that by doing this, the modeling becomes much easier, and the constraining power when combining all these different regions together is a big improvement when compared to the analysis that just mixes everything together from the start. In density split redshift space distortions, we find similar advantages in the sense that by splitting the density field in this way, the modeling also becomes easier. This is because when you look at the distribution of galaxy pairwise velocities in each of these environments, which is ultimately what describes the clustering, the distorted clustering patterns we observe, we see that the distributions are very close to a Gaussian distribution. This has to be contrasted with what you would get for the usual two-point correlation function measurements. Namely, if you just stack everything together from the start and you measure the distribution of pairwise velocities, you would find that the distribution is highly skewed at very small scales. Whereas if you start from this density split approach of throwing random centers and then splitting the density field, the distribution of velocities in each of those environments closely follows a Gaussian distribution. The advantage of this is that you can use relatively simple models, such as the Gaussian streaming model, to model these distortions. Here is a look at the redshift space cross correlation function for all the different density split quintiles. So usually I split the density field in 5 different quintiles that I label from DS1 to DS5, from low to higher density. And I also show the two-point correlation function on the bottom right for comparison. And same as before, the color maps show the amplitude of the correlation function as a function of the scales perpendicular and parallel to the line of sight. So you can see that for lower density quintiles, such as DS1, we have these bluish colors in the middle, which basically is telling you that there is a lack of galaxies in the interior of voids across these scales. And when we move towards higher density quintiles, these contours start to look red in the middle, which is basically telling you that the cross correlation function is positive near the center. Because in overdensities such as galaxy clusters, we have just so many galaxy pairs around the center of the potential web. And these mushroom-like features that you observe around 100 megaparsecs over H or so, these are the baryon acoustic oscillations that are basically an excess of clustering that was imprinted on the matter distribution from the early universe, as you already know. This is more clearly seen when we look at the monopole of the cross-correlation function. And here you would see the monopole for the different density quintals, and the BAO is nicely highlighted as these bumps or depressions on the correlation function around the scale of 100 megaparsecs over H. This information is actually very, very helpful when it comes to constraining the Alcock-Paczynski parameters, because it essentially provides a standard ruler that can be used to put constraints on the distortions along the radial direction of the galaxy pairs. As I said before, what we usually do in practice is to just decompose everything into multiples. Here's a look at the monopole, the quadrupole, and hexadecapole of some of the density split quintals. Namely, I'm showing here DS1 and DS5, which are basically the void-like environments and the cluster-like environments on the right. The marker here show measurements from simulations, and the solid lines show the best fit model to those measurements. The best fit model is actually coming from the Gaussian streaming model that I previously mentioned. And you can see the agreement for each of the multiples is quite remarkable, even to very, very small scales. Look at these scales here are below 20. And the agreement is still quite nice across all the different multiples. This is usually something that is very hard to achieve for the two-point correlation function. For density split, it is much easier to go to smaller scales and still get relatively accurate model predictions. These plots that I showed here are basically results from periodic n-body simulations. But I have also run tests on MOCs that mimic the survey geometry of post-CMAS low C sample. So essentially SDSS data release 12. Here again, I'm showing the monopole and the quadrupole of the cross-correlation functions of different density split quintals. The black dots are the measurements and the blue lines are the predictions from my model. And you can see that the agreement is also quite nice, even if we include the survey geometry to the problem, which is quite promising. This is still of ongoing work. I'm still missing the intermediate density quintiles, and I still need to carry out the likelihood analysis on the data sample, but hopefully within the next few months, I will have more results, so please stay tuned for that. When it comes to parameter constraints, we see that if we compare the standard approach of the two-point correlation function against the density split method under the same conditions, namely using the same range of scales and using the same model, the density split method improves the estimates of the growth rate by roughly 30%. And the improvement of the Alcock-Paczynski parameters is even better, is nearly 6 times as better as for the two-point correlation function analysis. This had already sort of been seen in the past when looking at the improvement you would get from voids alone. This study that I previously cited, in which they basically incorporated the information from voids and added it to the two-point correlation function, was basically telling you that the fact that these contours are rotated between each other means that when you combine them, the cosmological, the constraining power coming from these different environments is really helping to improve the precision on some of these parameters. In particular, the precision gain of the Alcock-Paczynski distortions is very, very high, because basically the multiples, most importantly the quadrupole, is really putting very tight constraints on what the degree of geometrical distortions can there be. Namely, this quadrupole here, and the fact that this quadrupole has these very sharp features around here, it places very tight constraints on what the values of the Alcock-Paczynski distortions can be. So this is why the improvement on the precision of the AP parameters is so high with respect to the two-point correlation function. Now here's the tricky part. This is the model we used to model redshift space distortions. This is called the Gaussian semi model, and it essentially provides a mapping from the redshift space cross-correlation function C of S here on the left to the real space correlation function C of R here on the right. And the C of R is convolved with the probability distribution for the pairwise velocities along the line of sight. But the trick here is that the model ingredient requires you to know the C of R here. And this guy is not so trivial to know for the density split case. For the two-point correlation function, you can actually predict the power spectrum from Boltzmann codes such as CAMP or class. So you predict the power spectrum from any given combination of cosmological parameters. Then you do Fourier transform and adopt some biasing prescription in order to get the correlation function for those given cosmological parameters. And you can do this relatively fast, so you can incorporate it in your likelihood analysis during the MCMC, and it's very efficient, right? For the density split case, this is not so direct because there is no clear way yet about how to predict the power spectrum for a given density quintile, for a given smoothing scale, for a given set of cosmological parameters from these Boltzmann codes, right? Maybe in the future there will be an easier way to do it, but for the moment, there is no easy way to do that. So one way around this is to measure this C of R from simulations. This is in fact what we have done in our paper for the tests we did. So basically we take everything from simulations that have a fixed cosmology, and then we just rescale the amplitude of those profiles according to the ratio between the amplitude of density fluctuations between our fiducial cosmology and the simulation cosmology. And we have tested that this is a good approximation, but there could still be some residual cosmological dependence that we are not properly taking into account when measuring this from simulations with a fixed cosmology. So what you really want to do in practice is to be able to predict C of R for any given set of cosmological parameters in a very fast way without having to rely on simulations with a fixed cosmology, right? So what we are doing for DESI at the moment is working towards building an emulator based on a suite of simulations that span more than 100 cosmologies at different epochs. So the idea is to train the emulator on those data points and then build something that will allow us to predict all the necessary model ingredients for the density split method a very efficient way without having to re-simulate this thing every time we want to predict something for a given set of cosmological parameters. This is still work that is ongoing, but we hope that within the next few months we can get more results when it comes to the performance of the emulator itself. This is just showing the cosmological dependence of the monopole of the DS1 and DS5 density quintiles, and you can see that the monopole responds quite abruptly to changes in cosmological parameters. So as you deviate from the usual values of the matter density from Planck, these monopoles can change quite abruptly, and you need to incorporate this into the analysis in order to take into account all the potential dependence on cosmology from this mapping here, right? Having that said,
can I ask a question before
sure.
you move on? So I'm wondering, I mean, where do you factor in the uncertainty in baryonic physics?
Good point. So what we have done for the tests of this particular paper, where we basically showcase the method, what we did was to start from simulations of dark matter and populate the dark matter halos with the HOD prescription. So basically assigning galaxies to dark matter halos based on the mass of those halos using a statistical approach, right? And I think this is the best one can do for the moment when it comes to getting catalogs of the volumes that will be required for surveys such as DESI or Euclid. So far, it's super tricky to produce hydrodynamical simulations with such large volumes that can generate those number of galaxies for the data sets that we will be working with. So the best we can do at the moment is to start from dark matter only simulations and paint galaxies in halos according to prescriptions that will be reliable, right? So in our case, we use HOD, but you can also rely on sham or other statistical techniques such as semi-analytic models and so on. But there is definitely always an uncertainty there when it comes to, are we really properly taking into account all the potential baryonic effects that could be affecting my clustering estimates? So this is definitely a field of research that is very active. And I think
I mean, right. So I guess just to, I mean, if it's not clear to everyone, so I guess the point is that the devil is, or to play devil's advocate, I mean, you always have a lot of information on a small scale, so you can improve constraints by including them, but also you introduce uncertainties by basically unknown baryonic physics, which, so it's not quite clear whether there would be, I mean, diminishing returns as you go. I mean, naively, there's a lot of information, but also there is more uncertainty.
That is correct. Yes.
And for example, I mean, the question is that if you assume like one way of populating halos with galaxies, but then use another one when you want to infer the cosmological parameters, then I mean, how much systematic error you find in your parameters if you use the wrong, basically, galaxy formation model. And I mean, on a small scale, this would become more of a problem. Basically, exactly where things are. Well, there's Gaussian information to be gained.
Most definitely, yes. And I think this is something that is particularly worrisome when you look at the density quintals with very high densities on a small scale, such as DS5. For voids, this is not such a big issue because you have very low galaxies at small scales. And we have shown in previous papers that for void statistics, by comparing simulations with full baryonic physics versus simulations with dark matter only, the statistics from voids do not change significantly. But this is certainly something that could be way more problematic for clusters where you go to small scales, but you also have all these different nonlinear evolution going on, which introduce all these uncertainties into your model. So definitely, yes, this is something we need to keep discussing and keep in mind when working with our models and try to find better ways of incorporating the systematic uncertainties in our modeling. Yes, so this is a very relevant comment.
Thank you.
Right. So having that said, yeah, I just wanted to mention that I have compiled all the necessary tools that you require to run the density split pipeline from the identification to the likelihood analysis in this package that is open source and can be found in this GitHub repository. So the package is the interface of the package is wrapped around Python, but the engine of the package for intensive calculations is written in Julia, which is a relatively new programming language that some of you might have heard of. So this language was launched about a decade ago, and it was designed for high efficiency and high performance. So the syntax is very similar to Python, so it's very easy to handle, but the speed it achieves is similar to C or Fortran, and it communicates very well with Python as well. So you can call functions from Julia with Python and vice versa, and it's quite nice. So I have compiled everything in this repository, and it has notebooks with examples on how to run the pipeline and so on. So if your research requires some of these measurements at some point, it is definitely available for you to clone the repo and give it a try. I have also released this other package that takes care of all the clustering statistics, namely the two-point correlation functions, but also the pairwise velocity measurements, namely the velocity PDF or the radial velocity profiles that you require for this sort of modelings in redshift space distortions. It's called Contrast, and it can also be found in GitHub. It's again written in a mixture of Python and Julia. And it's also fully available. It's relatively fast, not as fast as CoreFunc, which is the fastest pair counting that is currently out there, but it's definitely quite fast and can be used on multiple cores. So if you ever need to compute pairwise velocities or other kind of statistic for your analysis, you can also give it a try. Will, how much time do I have left?
5 or 10 minutes.
Okay, that's good. Okay. Now, apart from all these constraints to lambda CDM coming from redshift space distortions from density split, I think density split also opens the door to other interesting opportunities when it comes to constraining not only lambda core dark matter, but also alternative models of gravity. So as you already know, there's a whole zoo of modified gravity theories out there. And generally speaking, some of these modifications to general relativity often come at the expense of additional degrees of freedom in the theories, right? And these additional degrees of freedom are usually of scalar type. The consequence of adding these extra degrees of freedom is that you end up with additional forces that in some of these models people call the fifth force, right? The thing is, where's that here? Right. The thing is that gravity is very precisely measured within our solar system. So you cannot have any crazy fifth force because it just won't be able to reproduce the observed dynamics in our nearby solar system. As a consequence, these modified gravity models incorporate some screening mechanisms that suppress these interactions on scales where the Newtonian potential or the gravitational potential is deep, or the environment is the environmental density is high, and this makes the theory converge to general relativity on those environments. So examples of those mechanisms include the chameleon screening, the Weinstein screening, symmetron, dilaton, camouflage, just to give a few examples. So how can we deal with that? In previous works, we have shown that the matter distribution around cosmic voids can actually bypass some of those screening mechanisms due to the very low galaxy number density in the void's interiors. As I previously said, those screening mechanisms are usually triggered in very high density environments where they convert to general relativity. But if we look instead at underdense environments, we can unscreen those modified gravity effects and potentially come with observable things that we can potentially measure with future galaxy surveys. So in these plots, I'm showing the cross-correlation function between voids and the matter density field for two different types of void finders, the watershed void finder on the left and the tunnels void finders on the right. And what is interesting from these plots is that the voids in modified gravity theories, here in particular, I'm showing the N1 and F5 modified gravity models. These are just examples of NDGP, which is one of those brain world cosmological models on red, and on blue is F5, which is one of the Huan Savitsky FOFR gravity models. And you can see that these voids are more deprived of matter in their interiors with respect to general relativity voids. And the reason behind this is that the fifth force is actually unscreened in the void interiors for these alternative gravity models. And what the fifth force is doing is actually helping evacuate the voids of their matter. So in other words, the voids are being evacuated more efficiently in these alternative gravity models with respect to lambda CDM. Now the tricky thing is that we cannot directly measure the matter density profile around voids just like that, but we can indirectly probe the matter distribution around these environments using weak gravitational lensing. So lensing is a way to probe the matter distribution around structures. These plots in particular, each of those panels show the weak lensing tangential shear profile around voids using different void finders. So in this study, we have used 6 different void finders, and all of them show that modified gravity models have a stronger weak lensing tangential shear signal around the void edges. So basically, the imprint of modified gravity that I showed earlier that was present on the matter density profile can also be recovered when looking at the void lensing profiles, which is definitely very promising. So based on tests with embodied simulations, we have calculated the signal to noise at which we would be able to detect those modified gravity signals using void lensing in surveys with characteristics of LSST and Euclid in the future. We find that using some of those void finders, there is hope to put constraints or distinguish those models from general relativity at many sigma level. So for certain void finders and for certain gravity models, we would be able to tell apart these models from GR at a more than 10 sigma level for future surveys, which is definitely good. If you pay attention to the markers, you can see that some of those, the algorithm that performs best is the one that's called tunnels. These are not the 3D voids that we are usually familiarized with. These are actually 2D voids that are identified on the projected distribution of galaxies on the sky. In particular, these tunnels are basically circles that are completely devoid of galaxies on the inside and have exactly 3 galaxies on the edges. This is something you can quickly achieve used by running a Delaunay triangulation of the density field and finding the circumcircles associated to each Delaunay triangle. That's a way to get tunnels from a galaxy distribution. And in this paper with Chris Davis, 2020, we went a step further into this question and asked ourselves, is there an even better way of boosting the weak lensing tangential shear profile when using voids? We found that an even better way to do this is to actually identify the voids directly on the weak lensing maps themselves. Instead of using galaxy positions to identify the voids, we would directly use the weak lensing peaks as traces of those 2D voids. And by doing this, you can actually boost the weak lensing shear signal even more compared to the voids you will normally get with the classical approach of identifying them with the galaxy positions themselves. So this is definitely something to keep in mind if you are focused on getting constraints from weak lensing signals around the environments of different local galaxy density. These are my conclusions. In the first part, I have introduced a new method to analyze redshift space distortions in bins of fixed local galaxy density that we also call quantiles. The advantage is that the velocity field in each of those quantiles is close to Gaussian. This makes it relatively easy to use models such as the Gaussian streaming model in order to predict the redshift space cross-correlation function down to very small scales. So we have shown that we can improve the precision on the growth rate by roughly 30%, and the precision occupancy parameters by more than 6 times when compared to the standard approach of the 2-point correlation function. And this also opens the door to measuring modified gravity signals by using the weak lensing tangential shear profiles around the environments of different local galaxy density. Most notably voids, because in voids is where most of this on-screening of modified gravity theories would take place. Again, all the software that is required to run these tests can be found in my GitHub repository. And if you want to take a closer look at some of the results, here's the archive link for the redshift space density split paper. I think I'll stop here. Well, thanks again for the time and the opportunity to present my work.
Great. Thank you, Enrique. Okay, any further questions? Yep, Jesse?
Hey, I really enjoyed your talk. I'm curious about, for the density split investigation, did you look into, so I'm curious about the choice of like the smoothing scale and the choice of using a top hat function in that. Have you explored it all? Like,
Yeah, that's
you know, if changing that affects things, or if there's some optimal way to choose that smoothing scale, or if using multiple scales could get you more information?
Yeah, that's a very good question. So the smoothing scale is a trade-off between different things. I've tried a few different things, and I found that for this particular sample, which mimics the number densities and clustering of the CMAS sample, the results I would get would be similar when using scales between 15 and 25 megaparsecs over H. You cannot go to much smaller scales than 15 because the mean intergalaxy separation of this particular sample is around 12 megaparsecs over H or so. So if you use a smoothing scale that is smaller than the mean interparticle distance, you will basically end up with a bunch of empty spheres because you would measure the integrated density at a scale where there are basically no galaxies at all. So your smoothing scale needs to be well above the mean intergalaxy separation. On the other hand, if you measure the smoothing scale at a very big distance, such as this small plot here on the inside, where I measure the density profile at the scale of 80 megaparsecs over H, you will end up with a distribution that is just Gaussian, because at large scales, you don't expect to see these non-linear effects, right? So you need to place it at a scale where you would still get non-linear effects, but it cannot be smaller than your mean interparticle distance. And for this particular example, in which I've been working with BOSS data, I found that the results do not change as much if you go from 15 to 20, but as we are also dealing with very small precision here, you would see that the smaller scale you use, the smaller scales you use will give you even higher and higher precision, but at some point your model will just break down because the smoothing scale just won't be able to split the density field in a smooth way, because you will start running into this problem of shot noise. For future surveys such as DESI, where the number density will be much higher, there is a possibility of exploring smoothing filters that are smaller than that. This is something we are currently investigating with the DESI embody mocks. But yes, this does play a role into your analysis, so it needs to be chosen carefully in order to maximize the information you could extract from these samples. Does that answer the question?
Yeah, sorry, there's another question from Mike.
That's very interesting, Enrique. I was curious whether, the first part was talking about correlation functions in redshift space, and the second part was, or the little bit at the end, was weak lensing. And I think in the past people have combined these, right? Because you constrain the bias that way. So have you looked into that?
Yeah, that's my final goal. To be honest, I'd really like to, in the future, once I am comfortable with the modeling in each of these two approaches independently, to join them together into this sort of 3x2 PT analysis, which would be a way to measure one of the uncertainties into the model, which is the galaxy bias, right? So for instance, for this particular tests that I did here with these models, I assume that a very simple linear bias in prescription for the density split quintals down to very small scales. And I introduced some additional nuisance parameters to sort of tackle the problem of non-linear biasing at small scales. this is a way to do this, but in practice, it would be much better to combine the RSD information with lensing and get the biasing estimates from lensing itself. So yes, the future goal would be to do one full analysis with the data vector that will comprise both the RSD and the lensing part. This is the final goal of this thing from my point of view, but for the moment, this is still work in progress. I need to make sure that I understand the modeling from the lensing point of view too, because so far I've only done the likelihood analysis for the RSD component.
Well, as you probably know, our survey, formerly called CFIS, now called Unions, is getting up to about 3,000 square degrees in the Northern Hemisphere, which of course overlaps with Sloan, Boss, and DESI.
Yeah, that's definitely something I will keep my eye on
at some point.
Yeah, most definitely. There is also some interesting things you can do, like cross-correlating these density split quintals with CMB as well. This is something we've been discussing with Alex K as well. So this is something we would also like to try in the future, cross-correlating the voids and the clusters with CMB, lensing as well, using now this full abacus of different density split environments. Because people have already done this with voids and clusters themselves, but the full approach between a spectroscopic survey and CMB lensing will also be quite interesting.
Okay, thank you, Enrique. As there are no further questions, let me just thank you again, and see you all next week, everybody.
Thanks a lot. See you.
Bye, everyone.
Bye.
Bye.